So now we're going to look at hypothesis tests for one proportion. Plus, we're also going to practice some of our older stuff like outliers and a lot of normal distributions. Number one, the prom committee is thinking about changing the location of the prom. The new location is more expensive to rent, and for the increased cost to be reasonable, they would want to be fairly certain that more than 46% of the senior class would attend the prom. A survey of a random sample of 52 seniors found that 25 would attend if the site changed. Which of the following pairs of hypotheses should the prom committee test? So what are we doing research for? We need to know if we're going to have it more than 46%, right? So what we're doing the work for is to see if we have evidence that we have more than the 46. And remember, the work is always for the alternate hypothesis. Now, we can't build a model with a probability of less than 0.46 because we wouldn't know what to use. Is it 0.44? Is it 0.45? Honestly, all of those values have the same effect. So since 0.44, 0.45, and 0.46 are equally not greater than 0.46, we're just going to use 0.46 to build our model. So our hypothesis, our null hypothesis, is P equals 0.46, and we're testing evidence to see if we can say that it's actually greater, that we have convincing evidence that it will be more than 0.46. Number two, a research dermatologist believes that cancers of the head and neck will occur most often on the left side, the side next to a window when a person is driving. In a review of 565 cases of head and neck cancers, 305 occurred on the left side. What is the resulting p-value? So first of all, we've got a lot of p's going on here in stats, right? First of all, I'm going to get p hat, which is the value from my sample, right? So that's p hat. We had 305 out of 565, or basically 0.54 is a proportion. Now, I need to calculate a probability. So a p-value is the probability of getting this, assuming our initial model is not true. So we're going to need a p, not a p hat, okay? So remember, we never use p hat to set the hypotheses. So what should we assume about the proportion of injuries on the left side? Well, basically what we're saying is, well, actually, cancers really. What we're really saying is that there should be no difference. So our assumption is that there is no difference between the left and the right. And then that assumption would be P is 0.5. Our research hypothesis is that the cancers occur more often on the left side. That is more than 50%. So we're talking about the probability of cancer on the left side. We're going to assume it's just 50%. But we're going to test and see if this is strong enough evidence that it is more than 50%. So we want to find the p-value, the probability of getting the statistic we got, 0.54 or higher, given that p is really 0.5. So we can calculate the probability of getting that test statistic for 0.54. If you were doing this on the calculator, could you do normal CDF and just use the 0.54 and the 0.5 and then whatever standard deviation that is? Yeah, you could. But sometimes you're going to be asked to use to write it in this test statistic notation. So we're saying, what is the probability that z is greater than this? So p hat is 0.54, p is 0.5, right? And you can see all the top numbers match, so we're looking good there. So if p is 0.5, none of these with 0.54 are correct, right? It will have to be one of these two. So what's the difference between A and B? This is 2 times the probability that it's greater than the right. And that'll come in handy for a two-sided test, but this is a one-sided test. We're only concerned that it's greater than, not that it's different. So our answer choice is A. Number 3, a pharmaceutical company claims that 8% or fewer of the patients taking their new statin drug will have a heart attack in a 5-year period. In a government-sponsored study of 2,300 patients taking the new drug, 198 have heart attacks in a 5-year period. Is this strong evidence against the company claim? So We assume the claim that at most 8% have heart attacks, but we got to use just one number. I can't use 7% and 6%. So I'm going to use the 8% or 0.08. So my null hypothesis is P equals 0.08. Now, we're not worried about less heart attacks. We're worried about more heart attacks. So this is a one-sided test, and my alternate hypothesis is that it's actually greater than 0.08. Now we need to calculate our test statistic, which is the 198 over 2300, and we got 0.0861. So that's some evidence, but I haven't really calculated the p-value. That will give me tell me if that's convincing or not. So I need to calculate standard deviation, and I can go ahead and calculate the test statistic because you're expected to report this. All right, so I want to know the probability of getting a sample this high or higher, given that the true value is 0.08. So that's basically the z-score for that sample is 1.078. And if you put it in the Statlet, you can see it's 0.1406. So to calculate a probability with a normal distribution, we have to hit second. And you see that blue distribution right there, the VARS button. Then we go to normal CDF, enter. And our low value, our z-score is 1.078. So I'm going to do it with z-scores first. And if I didn't have infinity, let me go ahead and show you how to do that. You go 1. It doesn't like any number bigger than 1 there, apparently. That's just too much infinity. Then you hit the second button. Then you hit the comma, that puts the EE there. And then put 99, so that's pretty much infinity. Sometimes you guys with proportions, you're thinking you should put 1. No, actually put infinity. We're trying to use the whole curve. And then hit enter. And we get 0.14051. So it's very close to our answer of 0.1406. All right. So again, maybe if I had used 1.08, let me go ahead and do that. Second distribution. It does, by the way, you get credit for both answers, so don't freak out like, oh my gosh, it's not exactly the same value. You are allowed a little leeway on these answers, which is what makes grading so much fun. All right, so you can see here, oh, that's interesting. So actually, maybe I round it too much. All right, and then let's go ahead. So this is with z-scores. We had a z-score of 1.078, and then we have we can go ahead and calculate it with the actual value. So let me show you how to do that. Second distribution. We go back to normal CDF. And this time we're saying, what are we worried about? Well, we're wondering the probability of getting our sample size or more extreme. So don't put the 0.08 here, right? Because 0.08 is our hypothesized P. That's not what we got on our sample. We put what we got on our sample there. We're still going to infinity. But now we're putting in our mean, which is 0.08, right? And our standard deviation, which is very small, 0.00566. All right, see how that's 3 significant figures? That's why I like that one. Hit enter, and your probability is getting us much closer to our 0.1406. All right, so, okay, so we have the 0.1406 there. And that means that this is not considered unusual. 14.6% is not an unusual probability, all right? You're a little lucky, but you're not that lucky. So we're going to say, okay, that's not that unusual sample. I don't think I have enough to sue this company. So we're not going to go against them on their claim. We're not going to change our mind. We could have gotten a sample like that if it really is 0.08%. I mean, 0.08 as a proportion, or 8%. Problem 4. So we do need some practice with factors, levels, etc. So we'll do that now. So before taking an exam, students either went to bed at their normal times or were sleep deprived for 4 or 8 hours. Half of each group were given a caffeine pill before taking the exam. Determine the number of factors, levels for each, and the number of treatments. So the factors is we were looking at 2 different things. So we were looking at caffeine pills and bedtime, right? So the factors are bedtime and caffeine. You can see right here, Let me get my pointer. There we go, my nice, lovely laser pointer. You can see right here we have normal bedtime and caffeine, sleep deprived and caffeine. So the bedtimes are the top one, and then the second treatment basically is caffeine or no caffeine. All right. So again, then we look at the bedtime levels. We have normal, we have sleep deprived for 4 hours, and we have sleep deprived for 8 hours. All right. Then the question asks how many treatments. Now you're probably going, well, it's bedtime and caffeine. Well, technically, as you go to each subject, you're going to have to choose some combination of these, and we can create 6 combinations of these treatments. So, I forgot to tell you the caffeine pill levels. That's 1 caffeine pill and no caffeine pill. And then we have all 6 of these treatments. So we have 2 factors, bedtime and caffeine. We have one with 3 levels and one with 2 levels. And then we have a total of 6 treatments. Number 5. Given this histogram and using the most commonly accepted definition of outliers, what p-values would be considered outliers? This one's a little tough because it's a histogram, and you know how hard it is to tell what the values are. So we're going to have to just do the best we can here. So there are 16 data points. We're going to assume each cell here is 1 value. All right. But even so, even if it weren't, it still cuts up the areas so we can compare. So there are a total of 16 of these data points. And Q1 is going to be a quarter of the way through. So it's going to be between the 4th and 5th data point. So it's probably right here, right around 70. Q3 is going to be 3/4 of the way through, which is actually back here. It's between the 12th and 13th data point. And we're going to say it's about 90. All right. IQR, we're going to guesstimate is about 20. And then, now it could be a little bit smaller. I'd say the biggest it could be is probably about 20. And so we're going to test it and see if we can pull out any outliers. So the upper limit is going to be that 90 Q3 plus 1.5 of these widths, which is 120. All right. So that's probably the widest, roughly the widest that IQR is going to be. And you can see that we're already not, we're not getting any outliers here because this value right here is not as high as 120. It could be anywhere up to 119.9999 because when you get 120, what you do is you create another box for it here. So the lowest this value could be is 50, but it cannot be all the way to 60. So if we're looking at that box right there. Okay. And don't forget, we also calculate the lower limit, but you can see we're not even close on that. So we definitely don't have any low outliers. And it looks like we don't have any high outliers either. Number 6, a company has a choice of 3 investment schemes. Option 1 gives a $30,000 return on investment. Option 2 gives a 50% chance of return and a $50,000 and a 50% chance of nothing. Okay. Option 3 gives a 10% chance of returning $100,000 and a 90% chance of returning nothing. Which of the options should the company choose? So option 1 gives the highest expected return, right? 30,000 is greater than both. Option 2 gives the best chance of paying off the $40,000 loan, a 50-50 shot. And option 3 gives the only chance of paying off a $75,000 loan. So if you want to maximize expected returns, you'd go with option 1. If you want to pay off this loan, yeah, option 2. And if you need even more money, you got to go with option 3. So all of the above answers are correct. The moral is that the greatest expected value is not automatically the best answer. Okay, number 7. Which of the following is a true statement? Tests of significance, hypotheses test, are designed to measure the strength of evidence against the null hypothesis. Yes, that is the purpose of a significance test. We're trying to test a null hypothesis based on our sample, all right, our evidence there. See if we have really strong evidence or not to go away from the null hypothesis. A well-planned test of significance should result in a statement either that the null hypothesis is true or that it's false. Sadly, we will never know if it is true or false. It's very hard to prove something true. So we don't know, even if we go to the alternate, we're never 100% sure that that the null is not true. We just have evidence that it's not true. The null hypothesis is one-sided and expressed using either less than or greater than if there is interest in deviations in only one direction. The null hypothesis is almost always uses the equal statement because we use the null hypothesis to build our model. And so we need just one value. We don't want a range of values. That would be very difficult to build. Instead, we use one value, so the null. Now, the alternate, on the other hand, will go left or right, or even look at both of those, left and right of the value, so not equals. All right. When a true parameter value is farther from the hypothesized value, it becomes easier to reject the alternative hypothesis. We never reject the alternative, but it does become easier to reject the null. So if that said null, that would be a true statement, but it says the alternative. Increasing the sample size makes it more difficult to conclude that an observed difference between observed and hypothesized values are significant. Actually, the larger our sample size goes, the more the power, which is the ability to see the difference between your observed and your hypothesized values. So the true statement is statement A. Test of significance, hypothesis tests, are designed to measure the strength of evidence against the null hypothesis. Number 8, a kidney dialysis center periodically checks the sample of its equipment and performs a major recalibration if readings are sufficiently off target. Similarly, a fabric factory periodically checks the size of towels coming off an assembly line and halts production if measurements are sufficiently off target. In both situations, we have the null hypothesis that the equipment is performing satisfactorily. For each situation, which is the more serious concern, a type 1 or a type 2 error? So first of all, let's say, what is a type 1 error? A type 1 error only occurs when the null is true, but we think the alternate. So the way I keep track of this, type 1 is the first hypothesis, which is your null is true. How could you make a mistake? Oh, you think the other one is true. So let's look at the dialysis center and the towels. So for the dialysis center, the equipment works, but we think it doesn't. So we have to do a major calibration, even though it's fine. For the towel company, the towels are fine, but we shut down production. So those are type 1 errors. Type 2 errors occur when the second hypothesis, the alternate, is true, but we think the first one is. So for the dialysis center, the equipment really isn't working, but we think it is. All right. And then for the towels, we think the towels are off size, but we think they're fine. All right. So which one is worse for the dialysis? When the equipment's not working, that's dialysis. That's a serious thing, right? So if we think the equipment's not working, but it is, the good news is no one's getting hurt. But if you're doing a dialysis and it's not working, that means that's affecting someone's health. All right. Whereas for the towels, shutting down production is probably the bigger deal. Maybe it's okay if the towels are a little bit off, but it's worse to shut down the production line and then you lose profit. So we're going to say C, the dialysis center, type 2 error is worse, whereas the towel manufacturer, type 1 error is worse. Be prepared for questions like this, okay? Be prepared. You need to be able to tell the difference on these. Number 9, suppose you did 10 independent tests of the form the mean is 25 versus the mean is less than 25, each at the alpha equals 0.05 significance level. What is the probability of committing a type 1 error and incorrectly rejecting a true null with at least one of the 10 tests? All right, so the alpha is, you set that as the probability of a type 1 error. This is what you're willing to live with. You're saying, I'm willing to be wrong 5% of the time. So in this case, we're looking, what's the probability you make this error more than one or more times, right? So that's what we're trying to figure out. So we could go and calculate the probability of making one error out of 10. You could use a binomial distribution or something like that. And then you'd repeat for 2 or 10. So you could actually do binom of 1 plus binom with x is 2, etc. That's a lot of work though. Or you could say, hey, That's just a probability of, that's just 1 minus the probability of x being 0, no errors. So the probability of not making a type 1 error on one test, on one simple test, is 1 minus 0.05 or 0.95. But we're going to run these 10 times, so I need to go 1 minus 0.95 to the 10th, which is 1 minus 0.599 or 0.401. All right, so your answer is B. Number 10. Suppose you toss a fair die 3 times and it comes up an even number each time. Which of the following is a true statement? By the law of large numbers, the next toss is more likely to be an odd number than another even number. So the law of large numbers refers to averages of many, many tosses, not individual tosses. It doesn't tell you how many are needed either, so that rules out D, which says the law of large numbers tells how many tosses will be necessary before the percentages of evens and odds are again in balance. That would be interesting if it could do that. And then we have B and D are similar. Based on properties of conditional probability, the next toss is more likely to be an even number, given the 3 in a row have been even. And D says, wait, there's, it's, I think I meant C. Dice do actually have memories, and thus the number that comes up on the next toss will be influenced by previous tosses. That's pretty funny. No, it's pretty straightforward. The probability that the next toss will again be even is just 0.5. It does not change. Number 11. Jonathan obtained a score of 80 on a statistics exam, placing him at the 90th percentile. Suppose that 5 points are added to everyone's score. Jonathan's new score will be at what percentile? So first of all the scores are just shifted, all right? So I'm going to have my old z-score. I'm going to use z-scores to illustrate this because you can get percentiles from z-scores. So my old z-score is z equals 95 minus the old mean divided by the old standard deviation, right? And let's say I add, it says 95, but pretend I said add 5. Sorry. Here we go. Let me just go get rid of that pointer option. Little typo. We're not adding 95. We're just adding 5. All right. To all the scores. Note that shifting does not affect SD, so it stays the same. All right. Then we get a new z-score where we add, I'm doing, my new score is 100 because we added 5 to his score. Then we have to subtract the new mean. Well, the new mean is also going to go up by 5, right? The standard deviation is not affected because we just shifted, so I can just keep the old standard deviation. So if I say, oh, it's 100 minus the old mean, and I distribute that minus, I have minus 5. And then so 100 minus 5 is 95 minus the old mean, which is the old SD. Guess what? The z-score didn't change. So the percentile does not change. He's still at the 90th percentile. Number 12. To study the effect of music on piecework output at a clothing manufacturer, 2 experimental treatments are planned. Day-long classical music for one group versus day-long light rock music for another. Which of the following groups would serve best as a control for the study? So if we need the effect of music, then we also need to look at a work environment without music. That is our control group. So it would be a third group for which no music is played. So hopefully that one was pretty easy. Which of the following is a binomial random variable? So remember we had the bins. It has to be binary, it has to be independent, should be fixed number of trials. I really just checked bin, all right. So the number of tosses before a 5 appears when tossing a fair die. Well, it's not a fixed number of trials. This is geometric. You're tossing until success, all right? So it's not A. The number of points a hockey team receives in 10 games when 2 points are awarded for wins, 1 for ties, and no points for losses. Number of points is not binomial. It's taking on a range of values, all right? C, the number of hearts out of 5 cards randomly drawn from a deck of cards without replacement. So hearts is binomial, heart or no heart, but the probability is not independent because we're not putting the cards back in the deck. So C is almost there, but not quite. D, the number of motorists not wearing seatbelts in a random sample of 5 drivers. Well, it is binomial. They got the seatbelt or they don't. It is independent. We're going to assume people aren't looking at each other and saying, oh, they're not wearing their seatbelt, let me take mine off. Or they are wearing their seatbelt, let me put mine on. I think the difference would be is if a cop car came through traffic, everybody would make sure they put on their seatbelts. But that's not the case here. We're not too worried about that. Then finally, is there a fixed number of attempts? Yes, we're only looking at a random sample of 5 drivers. So D does fit the setting of a binomial random variable. Number 14. Company 1 manufactures demolition fuses that burn an average of 50 minutes with a standard deviation of 10 minutes, while Company 2 advertises fuses that burn an average of 55 minutes with a standard deviation of 5 minutes. Which company's fuse is more likely to last at least 1 hour? Assume normal distributions of fuse time. See how they told you it was a normal distribution? So that'll make our life easier. So Company 1, here are the parameters. So notice these are not statistics. These are population parameters. We know mu and we know sigma. So the probability it lasts greater than 60 minutes, if I do it on the calculator, which I'll show you in a second, is normal CDF, lower 60, upper infinity, and then put in the mean and the standard deviation. Company 2's parameters are slightly different. So I just basically, instead of 50, and I put in 55, instead of 10, I put in 5. All right, a little more normal distribution practice on the TI-84 second, distribution, normal CDF. So our lower in this case is 60 for the first company. Our upper is infinity, yeah, I get to keep that there. Our mean is 50 and our standard deviation is 10. Let me go ahead and hit enter. And our probability is 0.159. So let's go ahead and do the second company. Distribution, normal CDF, and our lower is still 60, our upper is still infinity, but our mean and our standard deviation are different for this company. And we get exactly the same number. So both have what we can look at is their z-scores. All right, so that is the answer. The z-score for company 1 is 60 minus 50 over 10. We're getting 1. The z-score for company 2 is 55 minus 50. We're again, divided by 5, we're again getting 1. So since both have the same z-score, they have the same percentile, they have the same probability. Which of the following is not important in the design of experiments? So control of confounding variables. No, that's kind of important. That's why we do control groups. That's why we do block design. A randomization and assigning subjects to different treatments. Super important to average out the effects of confounding variables. Those darn confounding variables. C, use one. No, we don't need more confounding variables. We're trying to minimize their effect. No, confounding variable, bad confounding variable. All right, then finally D, replication of the experiment using sufficient numbers of subjects. Larger N provides more precision and less variability. So the only one that is not important is C. All right, then I have a bonus on here. Someone was asking on the video lesson, where this part right here, why did I say half the p-value is 0.218? So I'm going to show you on the Statlet what's going on with this half a p-value thing. So on calculators, remember, we only do one-sided probabilities or probabilities in the region. But on the Statlet, we can actually do outside a region. So I'm going to plug in the lower z-score, negative 0.778, and positive 0.778, since I did all this work with the z-scores instead of the actual mean and standard deviation. So if I say outside of a region, basically you can see that what we're testing is not that they're more than or they're less than. We're testing, is it just not equal to that value? So the value's here. So being significantly more than is over here on the right, less than is here on the left. But there is no way to say normal CDF outside of a region. So how do we do it on the calculator? We usually say to the right of the value. So let's say I do that 0.778. And you can see there is part of it, but that's only the greater than value. We're actually interested in both the greater than and the less than values. And because of symmetry, both of these are going to be the same. We just double it. And that's it for your reflection. So